Good evening, everyone. Welcome to our YouTube live session on swarm intelligence algorithms for complex optimization problems, presented by the IEEE Computational Intelligence Society chapter under the IEEE Vardhaman Student Branch and hosted by the Department of Information Technology. Tackling complex optimization problems can sometimes feel like walking in the dark, but tonight we have someone here to show us the light. We are incredibly honored to welcome Dr. P. Sreedevi, ma'am, Associate Professor at RGMCET Nandyal. She is an exceptional expert who will illuminate the path for us, showing us exactly how to leverage swarm intelligence to solve these complex and intricate challenges. You will be having access to the live chat. If you have any doubts, you can comment down below. And Sridevi, ma'am, the floor is all yours. Please continue with the presentation.
Thank you, Srinivas, sir. First of all, a very thank to the IEEE Student Branch, CSI. Very warm welcome to the students of Vardhaman Engineering College. I thank to the people of whole team. Here today we are going to explore some new topics, interesting field. So I will share my screen. So today's our new topic is swarm intelligence algorithms for complex optimization problems and bio-inspired computing systems. So here, whereas the swarm intelligence, this is not the new topic where it is evolved in 1989, actually, where the nature becomes our teacher and computer learn from the intelligence of the living organisms. First of all, I will ask you some questions. Have you ever observed how a group of ants find the shortest path to the food? So actually we will see ants, they are going in some shortest path, going in a line,
Excuse
right?
me, ma'am. Sorry for interrupting you. Can you please remove the meeting window, the short one, so that viewers will have the full screen view?
Okay, sir.
On the there on the top right. Oh yeah, this is also fine. Okay, ma'am. Thank you.
Yeah. So we all know that ants go in a line, they will find a shortest path to the food. And one more, have you ever observed how a group of ants find the shortest path? And how does the flock of birds decide its direction? And we all see the nature, right? By observing the behavior of birds or animals, we will learn solving how the complex problems. So today I will explain what are spam intelligence algorithm for optimization problems. Wait for a while. Yeah. Here today we will cover what is spam intelligence, what are our core principles, mainly the spam intelligence algorithms like ant colony optimization, particle swarm optimization, artificial bee colony, firefly, cuckoo search, gray wolf and bat algorithms, and what are the analysis of these algorithms, where we will use these in real times. So we will use in this robotics, IoT and cloud computing, wireless sensor networks and so on. So what are the future trends, right? So coming to the point, what is swarm intelligence first? We all know no single ant, bird or bee is smart on its own, right? So first of all, but when thousands of them work together with following some simple rules, the group becomes smart. All we know this. So as a single, so we will do some, but as a group of together, we will solve many problems easily. So this is actually the nature. So Whereas coming to the swarm intelligence, here no boss or no leader is needed because ants follow their behavior, birds, and so on. Simply the thing is, we don't have any centralized approach in the swarm intelligence. Simply we call it as swarm intelligence is a decentralized problem solving approach. This is modeled on the behavior of the social organisms like ants, bees, birds, and fish. Here we will see the many simple agents that follow some simple local rules that adaptive to the global behavior. When come to the point, simply it is a decentralized. It is useful because it solves the problems that are any centralized or any complicated one based on the simple normal mathematical models. Why? How? We will see how it will solve based on because it provides robust, scalable, and adaptive solutions to the optimization problems. So, what is bio-inspired computing here? Bio-inspired means any computer technique that copied from the biology, not only just swarms, it copied from the biology, like our evolutionary algorithms, swarm intelligence, artificial neural networks, artificial immune systems. We all know DNA computing is nothing but a bio-inspired computing. So all these totally depends on the iterative improvements based on the feedback mechanisms. Popularly, these are based on such matters. How the single deterministic path will be. So coming to the swarm intelligence, that is today's our topic. This is just a branch of the bio-inspired computing. Sir, screen has shared, sir. No. Yeah, yeah, yeah. Wait for a while, sir. Yeah. So our swarm intelligence algorithm, that is only the some branch of the bio-inspired computing. No, see, what is the nature? Why look into the biology coming here? So first one is the ant colony. What the ant colony will do here? Ants that will find the shortest path between the nest and the food. It doesn't have any leader or any no map here, only based on the pheromone trails. Coming to the bird flocks. Once birds turn together instantly in huge flock without crashing. That is avoids the predators through local coordination. Right? Wolf packs. What is wolf pack here? So wolves hunt as a team with different roles, right? Based on the role-based cooperation. Even wolf doesn't have any leader. And coming to the bee colonies, balance exploring the new food sources without exploiting the new ones, known ones, right? So coming to the all nature, we have ant colonies, bird flocks, wolf packs, bees colonies, all came our nature. All these are the inspiration from our daily routines. So we will solve many algorithms easily based on our nature. The main example is these algorithms. Coming to a timeline of swarm intelligence, it will show us how these will grown over time. See here, in 1986, it started with some computer animation of birds flocking. And coming to the 1989, got its name as swarm intelligence. And then the researchers created some specific algorithms in 1989. And then in ant colony optimization, particle swarm optimization, so on. So algorithms are evolved. In 2005, bees colony optimization, very, very important in our research ABC algorithm. So that is evolved in 2005. And more algorithms like Grey Wolf, Fireflow, Cuckoo Search, BAT algorithms that are in from 2009 to 14. So very, very important topic for the researchers. So what are the four pillars for this self-organization? First one is the positive feedback. We don't have any centralized here. All are self. So simply calling it as it is the self-organization. What is the positive feedback here? Coming here, so we will get a good solutions. Good solutions are get rewarded and reinforced in the positive feedback. When coming to the negative, bad are old solutions that fade away from over the time. We all know this. That means that will prevent premature conversations to the poor solutions. When the next pillar, that is randomness, whenever we have some random exploring stops that will grow from getting the stacks. So the discovery of new potential better solutions to avoid the stagnation here. Coming to the multiple interactions, agents, that means the remaining the people that will share the information locally to get a good solution and to propagate the entire population. So all these are the four pillars for the self-organization. So we will discuss it one by one. So what is a stigmergy? Very important concept here. So it is nothing but communicating through the environment. How the birds, ants, um, flies that will communicate through the environment. Here, a mechanism of indirect coordination in which agents modify their environment and other agents react to that modified environment. How it will happen? So because animals that will don't talk each other directly, right? Instead, they leave some mark in the environment, and based on the reaction of that mark, automatically that will go into a flow. So an ant deposits some pheromone on a path. Later, the ant sends to the pheromone and more likely to follow the same path. So no agent is needed to know the whole system here because we don't have any leader, no agents, no centralized path. So just the local environment cues are enough to coordinate the thousands of the agents. Only the ants based on the pheromone, they are going to go with a shortest path. So many algorithms like ACO, where shared pheromone matrix replaces direct agent to agent messaging here. So first of all, what is the main centralized and the decentralized? I am talking about the decentralized approach today. So what is centralized? Coming to the centralized, it has just a single point of decision making and control. And it requires some global information to act right. We need some rules for the centralized. We need to follow those rules. We have some head, right? Single point of failure that fragile to the breakdown whenever we have a centralized. Difficult to scale as problem size grows. Whenever we have thousands of systems, automatically it is difficult to get a centralized. Predictable, but it is a rigid behavior in the centralized systems. But coming to the decentralized systems, many simple agents, no central controller here. So we all are as following some simple rules. We don't have any leaders. Agents acts on local information only here. Highly fault tolerant and robust here. It is naturally scalable to larger populations, adaptive, and it is emergent and the flexible behavior. So we are using in the optimization algorithms. Like what is the traditional optimization? That what is swarm-based methods. Traditional means that is it has deterministic and single path. Now coming to the swarm intelligence, so it is not a single path, it is a population based, it is a stochastic environment. In traditional environment, we often need some gradient, but it is a derivation free, swarm intelligence or derivation free, we don't require any gradient here. Coming to the local optima, the traditional algorithms are easily trapped because we have the centralized, we have a leader. Coming to the swarm intelligence, we have better global exploration and scalability. So degrades one on complex spaces. Coming to swarm intelligence that scales with parallelism. Swam intelligence are best suited in non-linear, NP-hard, and dynamic problems. Wait for a while, system has struggled. Yes. See, today we are going to discuss about this ant colony optimization, particle swarm optimization, artificial bee colonies, and some other algorithms. First, we will come into the one by one. First one is the ant colony optimization. Simply, so what is ant colony? We all know that ants wander around and leave some pheromone as they walk, right? So ants that take a shortest path to finish their round trip faster. So ants, they will search for a shortest path whenever they are walking to some food. We all know this. How? They are following the same line. Simply, they can lay some pheromone on that path more oftenly. Over time, more ants follow the stronger smelling path, and the smell on longer paths fades away. So, without knowing the whole map, the colony collectively converges to the shortest path. So, here, without knowing any whole map, the colony converges in the shortest path, right? That is the main result that we will get. How it is? So, based on the core mathematical formula, how it works. So, probably, so we will take an ant at node I, and that is moving to J. We know that I is the source and J is the destination. That moving from I to J from for the food. See, tau, that is a pheromone level on edge. Here we are taking the pheromone level, that is the edge T of J. Here alpha is the control weight that is given to the pheromone. So based on these, we have to take the heuristic desirability. Typically that we will take one, that is the distance from I comma J. And we have the beta, that is also the weight of the given to the pheromone. So after taking these, the T of I comma J pheromone and level of edge from source to the destination, we'll go with the summation. So what are the pheromone levels that it has? And we will go with the control weight. So based on this formula, that we are going to calculate what the colony optimization and what is the distance from the source to the destination. How it works based on the algorithm step by step. So coming to the first step. So ants that will starts with the random spots, and that will share the equal pheromone everywhere. That will lay the pheromone everywhere. Each ant, coming to the next step, that will each ant build its own path using the probability rule. Based on the probability rule, so it is going to build its own path. Next step, it will check how good or short each ant path was. Is it a shortest path or not? That is going to evaluate here. Next, after evaluating this, it will update the pheromone. That old smell fades or not. Better pause to get more new smell. Is there any deposit of the new pheromone? That will check the and update the path. And repeat this whole process many times until it stabilizes. That is the total of the iteration that we are going to complete. So then automatically it will find the shortest path based on the pheromone smell. So when you go with the pseudocode, first of all, we will initialize the pheromone for all the edges from source to destination while not stopping the condition. So ant colonies that will build the tour using some probabilities like simply P of I comma J. And it will record the tour length. So what is the shortest and what is the each edge? So what is the tau? That is the source to destination 1 minus tau to tau of I comma J. So here simply that is the initial pheromone level we have, and we have some the evaporation rate, and we will deposit the constant of pheromone constant, that is simply taking it is a Q. So and we have the number of fans. Often we will take some number of nodes in the wireless sensors and or our data points. Simply we will call it as the number of fans. We will, that is the M. Based on the iteration of steps. So based on the typical stopping condition, we will fix the iteration count. So Whenever we don't have any improvement for n rounds, we will stop the condition. So that is the ACO pseudocode. Where we use this ant-colony optimization actually. Coming to our real time. So it is a traveling salesman problem. We all know that traveling salespersons, they will find the shortest path to deliver, right? So we know that delivery companies and some telecom networks that use ant-like routing to constantly find the fastest path, even as a traffic or some network conditions change. So no one has to manually reprogram the system, right? Yes, it adapts on its own. So real companies, they will save money on fuel and reduce the network delays based on finding the shortest path. We all know this. So simply we are taking the example of the traveling salesperson problem. So not only this, any delivering companies or the telecom networks, so all they will use the shortest path. So to find the easy way of communication and the simply way of finding the complex solutions to the complex problems. So next is the network routing. Whenever the telecom networks they will deliver to fleets, they must continuously route the packets or vehicles through changing congested networks while minimizing the delay and the cost. So they will use the swarm intelligence algorithms. Next one more algorithm is the particle swarm optimization. So here, just we will assume the flock of birds or a school of fishes. No single bird is the leader, right? Yet they move together smoothly, right? Yes. So we'll observe these scatter particles that will random with the random starting of speeds, right? Birds flying in a flock or fish swimming in a school. They will adjust their positions based on their own experience. We know this, and their neighboring positions. What's the key insight for this? How they are flying in a flock without disturbing the line and so on so. Because it has each individual balances and it has some personal memory with some social influences. So here the particle swarm optimization has coined by Kennedy and Eberhardt in 1995. So simply model candidate solutions as particles moving through a search space with some velocity and the position. Moving in some speed, like we are going to calculate velocity and the position, right? So main the thing is scatter the particles randomly here with random starting speeds, and we have to check how the particles are in the current spot. Is it no or not? So it is going in a best direction or not? How it is? That means first of all we have to find the velocity of the particles. To find the velocity, we have V of t plus 1. That is W into V of t. Simply the formula we have C1 R1. So C1, C2 are the cognitive and social acceleration coefficients we have. And R1, R2, we have some random numbers in the stochastic. And coming to the P based, that is where the body is. What is the best position of the bird? So in the personal. Coming to the G burst, that is the global best position. Best position by the entire swarm so far. First of all, the main approach is we have to find the particle based and the global based. Which is the best position that we have? We have to personally found this. After this P based and G based calculation, we have to know the cognitive coefficients and the random numbers. Based on this, we will find the velocity V of t plus 1 and the position x of t plus 1 we will going to calculate here. So coming to the algorithm, how we are going to take this step by step in the process. First, we will take the initialization of the swarms, randomly place some particles in the search space with some velocities. And then we will go with the evaluation, how good each particle in the current position. And we are going to update the particles personal based spot and the swarm overall best spot. That is the global based. particle based and the global based. That is the main criteria here. And then we have to update the mission, that is each particle using a velocity formula, right? So v of t plus 1 and the position formula like x of t plus 1. Then we will update this and we will repeat this process until SWAM selects on a good answer. That means that will meet or find the maximum iterations reached. All these are because updates are simpler vector arithmetic here. Particle SWAM optimization is extremely fast for iteration and it is easy to parallelize. So many of the researchers, they will use the particle SWAM optimization. How the worked example here, how the minimizing a benchmark function, how we will take here. So simply we are taking some 30 particles at random position across some search domains. In the each iteration, we are going to pull some particles towards the one best and the SWAM's best found point. In the inertia way, that is gradually reduced over the iterations, right? Based on 20 to 30 iterations, automatically the inertia is going to reduce. And we have to go with the fine-tuned exploitation here. Here the SWAM converges tightly around the global minimum with some few hundred iterations. Then we will go with a commonly used test with the optimizer for the local minima and small enough for the fast computations. Next, the main applications where we use this particle SWAM optimization in the real time. Main approach is the neural networks. Whenever we have training artificial intelligence or the neural networks, particle SWAM optimization can tune the networks in internal settings without needing any complex or mathematical gradients here. It will train the deep neural networks and it will also use in the power grid systems. So that will both require the searching queue, right? So it will helps to decide how much electricity each power plant should generate to save cost and reduce the waste. So in these type of the optimization problems, we will use the particle SWAM optimization. How this SWAM intelligence helps here? Coming to the power systems, PSO optimizer generator scheduling and relative some power dispatch to minimize the cost. Fast convergence here. It will suit the near real-time reoptimization because as grid demands, network conditions are shifts, we all need this type of the optimization problems. Now coming to the next algorithm, that is the artificial bee colony. What is this artificial bee colony? We all know that bees, which that evolve and that will flies, that will balance this exploration and exploitation. That way hive forages for nectar and so, right? So we will discuss what are these main role in the hive. We have 4 types. Simply we are taking the 4 roles: employed bees, onlooker bees, scout bees, and food source. What is employed bees will do? It will each looks after one known food source and it will repeat back on its quality here. Employed bees, so after one known food source and report back on its quality. Coming to the onlooker bees, so it will wait at the home actually and choose which food source to visit based on what employed has reported here. So simply it will wait for the report of the employed bees. Coming to the scout bees, it will randomly search for the brand for the new food sources when an old one runs out here. So actually when the old one runs out, actually we have to go with the new food sources, right? So that is the scout bees performs. Coming to the next one more role, that is the food source. That is very, very important here, right? Because that will work for the food. Just represents one possible answer to the problem here. That means that will represent some candidate solution. Nectar amount that represents the solution fitness, right? So that means better food. If it gets a better food, that is a better answer for the bees. So based on the nature of these ant colonies, artificial bees, we are taking this optimization algorithm, natural behavior. So here in the ABC, this artificial bee colony algorithm, we have three phases like implied bee phase, onlooker bee phase, and scored bee phase. So what we have discussed in implied bees, actually it will search for the, it will looks after food sources, right? So each implied bee searches near its current food source for a better neighboring solution. What onlooker bees will do? It will wait at home and um, look for the implied bee report. Based on the report of the implied bee, it will take the probabilistically select the sources to exploit further. That means favoring the higher fitness sources. What the scored bees phase will do? So it will randomly search for the brand, right? So that means sources that fail to improve after a limit of trials are abandoned. So that means code search randomly for the replacements here. So this is the main three phases of the ABC algorithm. So what is the purpose of taking this ABC? Where we will use it in the real time. So this mainly used in the job scheduling. We all know that the job scheduling algorithms, how we have to schedule this. So coming here, manufacturing the plants, and we know the data centers that will assign large number of jobs, right, to limit the machines or servers to minimize the completion of time and cost. We have to schedule these things, and we have to allocate some resources to the employees or the jobs, that the process. Whereas in the resource allocation, we will use this artificial bee colonies because it has some implied bees, onlooker bees, and the scored bees. Based on the performance of all these things, so automatically we can schedule and we can allocate the resources. So main thing is it is applied in flexible job shop scheduling and cloud task allocations to reduce make span and improve machine utilization versus some greedy heuristics. And also it will handle some discrete combinatorial scheduling constraints that due to its flexible neighborhood search. So all these are the main real-time applications that will apply artificial bee colony algorithm, right? So what is this? Next one is the wider nature. What the inspired families? Not only these ant colony optimization, particle swarm optimization, artificial bee colony algorithms, we have many more algorithms that inspired nature based on the nature, like firefly glow, cuckoo tuning, wolf hierarchy, and bat sonar. We have many more tools, many more algorithms that will evolve based on the nature. So coming to the firefly. So what is attractiveness and what is the movement here? So here, when you see direct the equation, so what is attractiveness, what is fireflies decreasing with the distance, or so we can't understand it. Yes. So first we have to know fireflies actually that glow brighter attract towards them. I think all you see the fireflies. And the glow gets weaker the further away, right? So that means whenever we are in the dark mode, automatically it has somewhat solution. So whenever we have the brighter, that will get the better ones, right? So a little randomness is added, so it can still explore the new ones. Based on these firefly, so we can also apply in many real-time applications like image processing and so on. So first we will discuss how it will help to in the optimization algorithms. Coming to the equation here, it is attract beta of R, that means attractiveness between the fireflies. How much it is attracting based on the distance decaying with the distance R, beta of R. So that is attractiveness at distance 0, and how it is evolving into the light absorption, how it is in the dark mode. Like that, we will calculate the attractiveness between the fireflies. Next, we will find the positions, how the position it is, how the random walk term for the explorations and alpha dot gamma, that is. So based on this, the position x of I, xi of t plus 1, that is the position. Based on the position, that we will have to calculate what is the best one. So from where we will get the brightener, from where we will are getting the dimmer, right? So what is the worst solution, what is the good solution based on the positions. While getting a random walks, we are going to take this firefly algorithm. So what is the attractiveness between the fireplace? We have to find the distance. uh, and first we will take as a simply will take constant as a 0, and we are going to calculate the distances of the firefly attractiveness. So where we use it in the real-time applications first. So first one is the image processing and the feature selections. So actually we use it to pick out the most useful pieces of information from large data sets, right? Yes. For example, choosing which parts of an image or sensor reading actually matter for an AI model. We have to know this. So the model runs faster without without losing the accuracy here. That means we need some high dimensional image and sensor data that contains some many redundant or noisy features that slow down and confuse some machine learning models, right? So how swarm intelligence helps in this type of the image processing and selection process? How it helps? Simply, each firefly represents a candidate subset of the features. That means brightness that reflects the classification accuracy. We have to check that. Where is the brightness and where is the dimness? Based on that, based on the brightness, that we will get the classification accuracy. And we have to take the attraction towards the brighter fireflies. That will drive them to swarm towards compact and highly informative feature subsets. So that means we have to reduce the feature set size significantly, that maintaining or improving some classification accuracy. Without speeding up and downstream model training, we can't do it, right? So we have to apply directly to the image segmentation and multi-threshold selection for medical imaging. So who are preparing for the medical image processing as a major project of the research, you can go with the Firefly algorithm. So next one is the cuckoo search. How the biological inspiration can we have based on the cuckoo search? We all know that cuckoos are the sneaky birds, right? Yes. Simply, cuckoos lay their eggs in another bird nest because those are the snaky. So, if the host bird notices this, what it will do? The host bird will kick out the eggs, right? Because that is the other cuckoo's eggs. Simply, it will kick out the eggs. Yes or no? So that means the host bird destroy the egg or abandons the nest, maybe, right? So poor solutions are abandoned here and replaced with the new random solutions. So simply taking the nature behavior, because cuckoos are laying their eggs in the other nest. So that is nothing but the poor solution, right? That is abandoned, that is replaced with the new random solutions. That is driving diversity here. That means bad solutions are get thrown out and replaced with the new random ones. Simply it uses the levy flights, mostly some small steps, but occasionally one big jump here. Simply very meaningful one. Mostly it will take some small step, occasionally it will take a large jump. So this is the real foraging patterns of the many animals. We will see all these things, right? So what is the main benefit of taking this cuckoo search model here? The main thing is the mix of local refinement and long range jumps helps cuckoo search escape local optima efficiency. Without losing accuracy, we will find the local optima, that is efficiently we will identify this. That is the main intention of taking this cuckoo search. So where is the real-time application of this cuckoo search? Where we will use this? Engineering design optimizations. We will see some structural and mechanical design problems, right? minimizing the weight of truss or spring under some stress constraints. So that will involve some complex constraint and non-linear such spaces. In this type of the mechanical design problems, so we will use Kaku such. So these are used to optimize spring, beam and truss designs that will achieve lighter, cheaper structure that still satisfy all safety constraints here. So how our SWAM intelligence helps here? How? Like we flight steps that let the algorithm explore widely different design configurations quickly here. That is the main intention here. Because the constraints handling variance that will penalize the infeasible designs, that is guiding to SWAM towards valid or the efficient designs, that you have to go so and so, you have to say there and you have to go within some directions, right? So that will performs competitively against the particle SWAM optimization and the combination with the genetic algorithms and the classic constraint engineering benchmarks. Where coming to the engineering design, single algorithm is not efficient for the optimization. We have to take the combination of the optimization algorithms, like combining the particle SWAM optimization with the genetic algorithms. How it is? But we have discussed just now. The particle SWAM optimization means we have to find the particle based and the global based. Which is the best one, from where we have to find these? Particle based and global. After finding the particle based and the global based, we have to optimize, take the optimization. For this optimization, we are applying some genetic algorithms. That means the combination of particle SWAM optimization and the genetic algorithms that will give the best efficient way to to solve these complex problems in the structural and mechanical design problems. So this is the main real-time application of this Kaku search. And next more, that is the gray wolf optimization. What is this gray wolf optimization? So we all know the hunting, right? Wolves hunt their hierarchy. So wolves hunts based on the path like alpha, beta, delta, and the omega. How these best solutions that we'll find? So first step is the alpha. What it will do? It will find the best solution found, and it will lead the packs on encircling and attracting the behavior of remaining animals. Coming to the next step, it will take the beta. What second step of beta that will do? Second best, that will helps to the alpha. That means the best solution that given by the alpha that will assist in the decision making and guiding the pack. Right? That the beta will do. What about the delta in the next step? That is the third best actually. The scouts and guards, we know this, right? So that will dominate omega wolves and scouts and guards the pack. That is the delta step will do. What about the omega? Omega is overall the best. That is who simply follow the top three, like alpha, beta, delta, that will follow all the three. So that it will get the best stance. So that is the optimum one. So based on these hierarchies, the wolf will hunt, right? Like alpha, beta, delta, and omega. Whereas coming to our optimization problems, first we have to find the best solution, and then we have to find the second best solution that based on assisting of the first one. And we have to find the third best solution, and the remaining we have to get the optimum one. Like that we have to solve our optimization problems. So this is the nature of inspiring that we have taken from the gray wolf optimize. Where we will apply this real time. We will apply in the feature selection and the fault diagnosis. Very, very, very important, the fault diagnosis in the sensor, in the networks. So industrial fault detection systems that must quickly identify the most diagnostic sensor features. Because whenever we have the centralized, when sensor fails, remaining all will fail. But so that we are not going for the centralized systems. We are taking the decentralized approaches. Okay. So most diagnostic sensor features from large noise multivariate time series data we have. So in this fault diagnosis in the network analysis, simply you can go with the gray wolf optimizer. You can take the algorithm. because it improves fault classification accuracy while cutting the number of monitored sensor features. So the researchers who are doing this sensor network problems, research problems, simply you can approach this Gray Wolf optimizer algorithm. So it will reduce your computation time and your hardware cost. So how these SWAM intelligence helps in the Gray Wolf optimizer? So we know that rules that will candidate the feature subsets, encircle that we have optimal subset, right? So like your particle based, global based in the particle SWAM, whereas in the Gray Wolf optimizer, we have the candidate features on the optimal subset that will guided by the alpha, beta, and the delta based solutions. What I am saying here is we have to find the not only the single optimal solution, we have to find the first best solution, second best, third best, and overall the best solutions that we have to identify. Then it is easy to make the to get the solutions. So that means few tunable parameters like make, Gray Wolf optimization that simply deploy in the diagnostic systems. We all see so healthcare data. So whenever you are going to the diagnostic systems, that is a very trending topic, right? So then you can also use this type of the applications. Strong balance like exploration and exploitation, that's fast changing in the sensor environments. All these are the real-time applications of the Gray Wolf optimization. Next, one more important is the BAT algorithm. What is the BAT algorithm here? We see the bats, right? In our nature, we have many bats. So, bats see in the dark. Yes, that will see only in the dark. Yes, that uses in the echolocations. So, sending out sound pulses and listening to the echo in the medical field. So, here in this analogy, each bat is a candidate solution like pulse frequency and loudness module step size and randomness of the movements. So simply a bats get closer to the prey that will get a good solution. Loudness decreases and pulse rate increases. This is the dynamic tuning that we are performing in the medicals, shifting from exploration to the exploitations. So based on these bats, that is that we'll see in the darkness, simply our doctors, I mean, daily in the medical field, they are taking the based on these bat algorithms, they are performing these the steps, modulation steps. So this main real-time application that we will use it in dynamic economic dispatch, antenna array designs, image compressions, right? So there are many real-time applications that we have. We know the bad closures that we will get a good answers here. Next, we will see the comparative analysis. So what all the algorithms choose the right tool. So up to now we have discussed about ant colony, particle spam, artificial bee colonies, fireflies, cuckoo search and grey wolf, right? What are the main, what are the comparative all these where we have to use? So coming to the ant colony optimization, we have taken the inspiration of the ants, right? So the main key strength is, so we will find the shortest path problem. The common use is routing, traveling salesperson and scheduling. Coming to the particle swarm optimization, that is mainly the inspire of bud flocking, particles and swarms, right? Fast convergence, the main key strength, and the few parameters we have in the particle swarms. So the main common use case is the continuous function tuning. Whenever you need this type of the function tunings, so you need to apply particle swarm optimization. Next is the artificial bee colony. So that we have taken the inspiration of the bees foraging, right? So the main strength is strong explore and exploitation balance here, where we apply this ABC, that is job scheduling and the numerical optimization. Coming to the firefly, one more algorithm. So we have taken the inspiration from the firefly attraction. The main key strength is good for multimodal problems. You can apply wherever you have feature selection and the image processing techniques. And one more algorithm, cuckoo search. So that is the main thing is the brood parasitism. That is the levy flight. So the main strength is escapes local optima well. The common use case is the engineering design. Next algorithm we have discussed is the gray wolf. That is main, we have taken the inspiration from the wolf pack hierarchy. So main strength is simple, few parameters. And the main use case is feature selection and the fault diagnosis. So all this is the main map today's our session, main map of our session. We have to check which algorithm, which optimization algorithm, in which case that we have to apply. We have to know all these type of the algorithms that are trending in our now. So what are the main strengths and limitations of this SWAM intelligence? So the main strength is it is a derivative free. It is a decentralized approach. It works on non-differentiable and noisy objectives. Right? So it is naturally parallel and distributable across the computer nodes, simply right computing the nodes. And very, very simple thing is it is the individual agent. When it is a decentralized, right, robust to individual agent failure or noise, whenever the single agent failures, no problem with other agents, that automatically works well. That is the main strength of this SWAM intelligence. So mainly it is effective in NP-hard, combinatorial, and the multimodal problems. And it is simple to implement, and it is adapted to the new problem domains. So whatever the strengths we have the limitations also, right? So the first thing is that no guarantee of finding the global optimum. Because from the nature that we are assuming that is a particle based, this is the global based, and we are calculating in the nearest future. But we don't giving a guarantee of finding this the global optimum. And it is performance sensitive to parameter tuning like alpha, beta, right? So weight function. So all these are the sensitive parameters. So when it is this is one of the limitation here. And it is converged prematurely on deceptive landscapes. And computationally it is heavier than the simple heuristic because optimization algorithms that all works on the formula. For small problems, so we can't go with the heavy calculations, right? So whenever you have that is a complex task, you can go with a SWAM intelligence. So theoretical convergence guarantees are limited here. So what are the main real-time applications where SWAM solves problems happening right now at the scale here? Vehicle routing, right? Whereas in the e-commerce applications, many delivery boys, right? So e-commerce companies, they will use the shortest path to find the routes of hundreds of vehicles, right? 2000s of addresses daily adapting instantly to traffic cancellations and new orders, taking the orders. So companies like some large parcel carriers report to the meaningful reductions in total distance driven. And to save the fuel cost, they will use SWAM-based route optimizations. Right? ACO, anti-collision optimization, and particle SWAM optimization, hybrids, and the combination of both algorithms continuously that will take the optimization of routes and newly deliver the request streams here. So remember that single optimization algorithm that works well but not most effective. If you want to get the most effective research problems, you have to take a hybrid and you have to take the combination of the algorithms, right? So SWAM based solvers that will handle the time windows like vehicle capacity, multi-depot constraints simultaneously. And we have distributed SWAM computations that keeps so replanning fast enough for near real-time dispatches. All these are the real times. And next one more is the robotic SWAM coordinations. So warehouses like Amazon, we will see that we have more big companies that has some warehouse and search and rescue robots that need to move around, right? So they have to avoid bumping into each other and avoiding collisions and cover an area efficiently without have centralized controls. All without one central computer controlling very single robot like PSO style, particle swarm optimization styles, and colony optimization style rules. Let's robots coordinate just by reacting to their neighbors and leaving markers just like the biological version, because we have seen the ant colony optimization, ants they will leave the pheromone that will leave the marks to come the state with the remaining ants, right? The same thing here, the robots coordinates by reacting their neighbors to the marks based on the marks here. So whereas in the PSO based flocking and ACO based synergy, so based on these algorithms, so robotic swarm coordination that will be in the real times. So deployed in automated warehouses, right? So order picking robot fleets and disaster response robot teams for efficient area coverage. Next, one more research area, that is the wireless sensor network optimization. So whenever you have battery powered sensor nodes that will relay data based on the data, because energy efficient optimization is very, very, very important in our nature. So because we all are using mobiles and much data, right? So we are transferring much, or not only the simple text messages, we are taking the videos, right? So for good morning, we are sending some animation. We are not satisfying with some text message for the good morning, right? So we will send some um, animation. That means we are using much batteries, data, right? So we have to consume our energy. Energy efficient is very, very important. So in this adapting to node failure in real time, we have to take the situation, we have to take the fault tolerance, right? So because whenever the single node failures, it extends overall network lifetimes, and we have to improve our data delivery reliably in some like smart agriculture, environmental and industrial and IoT deployments. We have to check all these delivery rate. So very, very important is the energy efficient optimization algorithms in wireless sensor networks. So how this swarm intelligence helps in these wireless sensor networks? This particle swarm optimization, artificial bee colony that will take some cluster heads, that means that will group the similar points and will choose as a cluster, one member as a cluster head to balance this energy consumption. Because whatever it has to communicate with all the cluster group nodes, so it will take much energy. So that it will communicate only with the head. So that it will group the similarity like a cluster, and it will point one node as a head, and it will communicate to save the energy in these algorithms. So ant colony optimization in this based routing finds it has energy efficient because it has multiple hop paths to adapt the nodes. So it is a problem whatever the nodes fails, so that we will go with the multiple hop paths in the energy efficient based on the anti-colony optimization. Like these swarm approaches, this decomputes the fast enough to react to a dynamically changing network topologies. So very, very important of the wireless sensor networks optimizations. Next one is the cloud load balancing and the task scheduling. We know that cloud data that enters must assign incoming computing tasks, right, to virtual machines, because we have to improve the resource utilizations and we have to reduce service level agreement violations that will compare to the round robin or the greedy scheduling. So whereas in our real time, we have to minimize our latency, cost and energy use. So whereas in the cloud load balancing and task scheduling, we will use such type of these swarm intelligence algorithms like ABC and PSO schedulers that will pre-task to the virtual mission assignments, and we will assign some candidate solutions evaluated, and we have to find the cost or latency fitness. Based on this swarm method, adapts quickly. So to busty and unpredictable workloads without needing any pre-trained models, we'll simply go with this type of the swarm intelligence algorithms. So again, I am saying this hybrid swarm plus some machine learning approaches that will predict the demand whenever we have the swarm logic handles the assignments itself. Not only the single algorithm that works efficient. So go with a hybrid algorithm. So now coming from ants to here we came to the autonomous drone swarms, right? Yes. So coordinating to the drones fleets for surveillance. So like agriculture or light shows, some must maintain the formation, right, to avoid the collisions. So without maintaining the information, I mean drones will collide each other, and right. So we have to avoid the collisions and cover we have territory efficiently in our real times. So main thing we will use some particle swarm optimizations or gray wolf optimizers or firefly algorithms. So that are used in the autonomous drone swarms, because it will enable large scale synchronized drone displays, and it has resilient agriculture or surveillance coverage without a single point or failure. How it helps? So we know that particle swarm optimization that will go with the best position, right? So based on the velocity and finding the new position, so the velocity rules that will keep drones in information that responding to the environmental changes like wind or obstacles. So that will find the positions and that will adjust the position based on the collisions, right? So this particle swarm optimization will helps in these drone swarms. Not only this, gray wolf and firefly that will variance optimize the target tracking and area coverage fast dynamically. These are the decentralized control that will means that will spam keeps functioning even if individual drones drop out. So from where we came from the ant colony, from ants to our drone swarms, right? Next application is the smart grid, and this is the renewable energy and also we will use in the renewable energy optimizations. So power grids like variable renewable output input that must balance the generation, storage, and demand in real time to avoid instability. So we will find these in the grid operators integrates that more renewable energy while maintaining stability and lowering overall generation cost. We will use these swarm intelligence algorithms. What are the main challenges and open research issues? Simply, main thing is the performance, right? Performance often depends heavily on hand-tuned parameters, so which don't transfer well across the problem times, right? So main things, FAMs can collapse onto suboptimal region too early, especially in high dimensional or deceptive landscapes. This is the main challenge. So without collisions or without collapsing any nodes, we have to get the best performance, right? So and also one main thing is the scalability. So very large scales are high dimensional problems, strain computation time, and you have to find the memory for population based search. That is also the main challenging. What is the limited theory you have? We have rigorous convergence proofs and performance guarantees remain an active area of academic research. All these are the main challenges for the researchers. What are the future trends in this swarm intelligence? So we know quantum, right? So the very trending topic, quantum inspired swarms. Combining quantum computing concepts with these swarm algorithms, so we will get for exponential speedups on selected problems. And not only this quantum, swarm plus deep learning, using these swarm algorithms to optimize neural architectures on hyperparameter search scales. And the hybrid meta heuristics, merging two or more swarm algorithms, so to combine the complementary strengths. Next trend is multi-agent real-world integration. Tighter integration with some IoT, edge computing, and physical robotics swarms for live decision making. So you can go with this swarm intelligence. So that means you can merge swarm intelligence algorithms with any trending topic. So what are the key takeaways? So first one is the emergence over control. So that means complex adaptive problem solving can emerge from the many simple agents. That means we have to follow the local rules. So we don't need any central, no central planner is required. So we go with simply decentralized. We have the rich algorithms like ACO, particle swarm, ABC, Firefly, Cuckoo Search, Grey Wolf, and BAT. So each has a map, a distinct natural strategy to distinct class of optimization problems. Based on the just natural behavior of animals and the ants, simply we are going to solve our optimization algorithms. So this is the proven real world value. These algorithms already power logistic routings, robotics, cloud computing, energy grids, and more today. So, what is still evolving here? Hybridization with deep learning and quantum computing is opening the next generation of bio-inspired optimization. That means we have to go with the still evolving search. Thank you. Any queries?
Yeah, I'm looking at. I don't think we received any queries. We'll proceed with the session.
Yeah, okay, thank you.
Raja sir, welcome sir. I didn't want to stop ma'am in the middle, so I didn't couldn't say hi to you.
Yeah, no problem. Yeah, Srinivas, how are you?
Great sir, great
Mm,
sir. How are you sir?
Yeah, going on these lectures.
Yeah, yeah sir. Monthly, once a month we are doing so.
Yeah, yeah. Convey my wishes to Nikhila ma'am. She is actually doing very nice on
Yeah sir.
behalf of
She
students.
she
Yeah,
too came into the meeting, but due to some other work, she left. I think.
yeah, yeah. So just convey my wishes to her. Okay.
Yeah sir. Yeah sir.
Actually, she's
Just
doing without any expectation, without expecting from you. She's arranging very nice lectures and getting some resource persons
yeah.
like
Yes sir.
Sridevi like this. Okay. Dr.
Yeah
Sreedevi
sir.
is actually my colleague and companion in teaching subjects. Okay.
Okay.
And
Okay.
yeah, she delivered very nice lecture today. Okay.
Yeah sir. It was awesome. Wonderful.
Yeah, 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 yeah. Nice, Sridevi. Okay. Okay. Thank you.
Oh, okay
yeah,
sir.
thank you, sir.
We'll move forward. So audience will move forward with the vote of thanks. Sridevi ma'am, Sridevi ma'am, that was an incredible and insightful and engaging session. On behalf of the IEEE Computational Intelligence Society chapter and the entire Vardhaman College and its student branch, I want to extend a massive thank you to you, Sridevi ma'am, for sharing your valuable time and profound expertise with us tonight. You have truly demystified the complexities of swarm intelligence algorithms and given us a clear light to follow for tackling optimization problems. Also, I would like to express our special and sincere gratitude to Dr. Rajakumar sir and Dr. Imam sir, who have been absolutely instrumental in making these webinars a success. Thank you both for your invaluable support, guidance, and for continuously bridging the gap to connect us with such brilliant and inspiring speakers every month. We are also deeply grateful to our college management for their unwavering backing. Thank you to our head of the institute, Professor JVR Ravindra sir, our professional head, Dr. Sangeetha ma'am, and our faculty advisor, Dr. Nikhila ma'am, for empowering us to host these enriching events every month constantly. Finally, a big thank you to all of you in the audience for tuning in, for participating in this webinar, and making this a huge success. If you found tonight's session valuable, please make sure you comment whatever queries, if you have any, and we'll surely answer them. We'll arrange some sort of medium to answer those questions. Thank you, everyone. Have a great night.
Okay, thank you, Srinivas sir and Nikhila ma'am and the whole team for giving me this best opportunity as a guest speaker today. Thank you, sir.
Thank you, ma'am. We should thank you for accepting our webinar invitation. Thanks a lot, ma'am.
Yeah, sir, always it's pleasure.
Thank you, ma'am. Thank you.